Thank you for inviting me. My focus today will be on collecting of meteorites. I brought along a portion of my collection. You can examine it after the lecture. But first, a bit of science. Why is the science of meteorites important? Well, it's because meteorites tell us where we came from. This reminds me of a story of a little girl who went to see her mum and asked her, "How did we ever get here?" Her mother replied, "First God created Adam and Eve. They had children. Their children had children. And so on and so forth, right down to the present generation." But children being naturally curious, the girl went and asked her dad the same question. He replied, "Meteorites brought us water and organic molecules. This led to the formation of bacteria. These eventually evolved into mammals. Some of these mammals became monkeys. Some of the monkeys were smarter than the others, and they became human beings." Well, this really upset the little girl. She went and confronted her mum and said, "You told me we came from God, but Dad says we came from a bunch of monkeys." To which the mother answered, "Don't worry, dear. I told you about my side of the family. He told you about his side." Well, tonight I'm going to tell you about my side of the family. So 4.6 billion years ago, there was no sun, no planets, no solar system, just a cloud of gas and dust. A nearby star exploded. This caused the cloud to collapse. Most of the mass went into the sun, the rest into a rotating disk. Imagine the dust in this disk is sticking together, first electrostatically, like dust bunnies in your house, then by gravity. Pebbles grow into boulders, boulders into protoplanets, and eventually into planets. So here is Jupiter. It's 320 times the mass of the Earth. As the planets formed, Jupiter's massive gravity prevented the debris in the asteroid belt from coalescing. This is due to what we call orbital resonances. Note that the asteroids further from the Sun, that is closer to Jupiter, retain some water and organic molecules. We call these carbonaceous. These molecules possibly could be the starters for life on Earth. Those asteroids closer to the Sun are mostly metallic and rocky. So how do meteorites fall to Earth? Not all asteroids we see here are orbiting in the asteroid belt. Due to collisions and gravitational interactions, occasionally a fragment of one of these strays from the asteroid belt and intersects the Earth's orbit exactly, and hence falls to Earth as a meteorite. Radiometric dating shows that most meteorites formed about 4.6 to 4.4 billion years ago, the very beginning of the solar system formation. The only exception is those meteorites blasted off of the Moon or off of Mars, many of which are much younger. That's when volcanism was still active on these planets. So 65 million years ago, if you were a dinosaur, that for you was a very bad day. That day, a meteorite about 10 kilometers in diameter impacted the Earth, causing a global ecological catastrophe. Other large meteorites have impacted the Earth in the past. For instance, the Sudbury Basin, approximately 2 billion years ago. By the way, the Sudbury Impact Basin is the second largest impact basin known on the Earth. Every few hundred years or so, a medium-sized meteorite falls, one that can flatten a portion of a large city. For instance, in 1908 in a remote part of Siberia. So how do we know that a meteorite made the dinosaurs extinct? In 1980, the KT boundary was studied, first in Italy and then all over the Earth. It's been radiometrically dated at 65 million years old. It contains a very high proportion of iridium. Iridium is rare on the Earth because most of it has sunk to the core of our planets, but it's much more plentiful in meteorites. Above this KT boundary, no fossils have been found. Below this KT boundary, dinosaur fossils are plentiful. Also in the 1990s, a crater whose size and age matched that of the impacting meteorite, was found in the Yucatan area of Mexico. The KT boundary is visible all over the Earth. Here it's shown in the yellow dotted line. In this photograph we see it at Zahersky Point in Grasslands National Park in southern Saskatchewan. Go there and bring some home. In a lab you'll find traces of the meteorite that killed the dinosaurs. So when did we realize that meteorites come from outer space? Until about 1800, scientists were unconvinced that meteorites are extraterrestrial. For instance, some scientists thought they were condensed volcanic dust. Thomas Jefferson, shown here, who by the way was well versed in science, was asked to comment on a Connecticut meteorite fall. His answer was, "Gentlemen, I'd rather believe that two Yankee professors would lie than believe that stones fall from heaven." All that started to change in 1801 in Palermo, Sicily. Astronomer Giuseppe Piazzi discovered the first asteroid named Ceres. This showed, apart from planets, there were rocks floating in space. Then in 1803, in Normandy, France, this occurred. A shower of 3,000 fragments fell on the town of Les. This was investigated by the French Academy of Sciences. Also around this time, English chemist Edward Howard showed by chemical analysis that meteorites have unique chemical and mineralogical composition compared with Earth rocks. So where are meteorites found? There are approximately 60,000 known distinct meteorites at present. Here's a chart showing where they're found. Why are so many found in Antarctica and in the deserts? Well, most meteorites are dark. That's because in their flight through the atmosphere, there's a dark fusion crust that forms on them. So they stand out against the white snow or the light-colored sand. Also in Antarctica, the movement of the glaciers concentrates the meteorites in certain areas, and Antarctica being a desert, the wind exposes these meteorites. By the way, Antarctic meteorites are not for sale. They belong to the governments that found them, usually USA, also Japan and European Union. Out of the 60,000 known meteorites, only about 1,100 are called falls. That means somebody witnessed the meteorite falling and recovered some fragments of it. The rest of these 60,000 are known as finds. So how are meteorites found? If a fall is observed and its approximate location is known, a search party is organized. Here's one about 2.5 years ago near St. Thomas, Ontario, organized by Professor Phil McCausland of University of Western Ontario. Notice that each of us is carrying a wooden stick. On the end of the wooden stick we've attached a small but very powerful rare earth magnet. Approximately 90 to 95% of meteorites are very rich in iron and nickel, easily picked up by this type of magnet. You can test out my hunting stick after the talk. I brought it along with me. So how do you spot one? There are websites that show that describe the visual characteristics of meteorites in detail, but basically they look out of place. Their shape, their color, their texture. Even the rocky ones can contain between 10 and 30% iron nickel, so are easily attracted to these rare earth magnets. Every 3 months, the Royal Ontario Museum has a rock clinic, so if you think you found a meteorite, bring it in for an expert opinion. 94% of meteorites are what we call stony, and these usually fragment high above the ground and scatter on the ground in an ellipse called a fall ellipse or strewn field. There are some published fall ellipse maps. Here's one from 1960 near the town of Bruderheim, Alberta. So if you plan on going hunting, try to get your hands on such an ellipse map. Another example of a hunt is the Buzzard Coulee hunt near Lloydminster, Saskatchewan in 2008. This was a very prodigious fall. Hundreds of fragments were recovered, totaling 41 kilograms. If found, who owns a meteorite? In Canadian law, the property owner owns them, but on Crown land, it's the finder who owns them. So if you plan on going hunting on private property, first get permission from the property owner. A good tactic is to offer to split any proceeds of any find that you make. To export meteorites out of Canada, you'll need an export permit. How can we pinpoint a fall ellipse? Well, eyewitnesses can observe a fall. Here we see a fireball near Banff, Alberta. Some are so bright they can be seen during the day. In order to survive the fall to Earth, the meteorite usually has to start out in space larger than a grapefruit, because usually 90 to 90% of its mass is vaporized in its flight through the atmosphere. On this photograph, the top of the streak usually starts at about 100 kilometers altitude. The endpoint, where the meteorite fragments, is usually in the neighborhood of 20 kilometers altitude. Based on this photograph alone, if I were to ask you where the meteorite fell, you could be off by 100 kilometers or more. But with multiple photographs or multiple eyewitness accounts, we could pinpoint the fall ellipse better. Out of the 1,100 known recovered meteorite falls worldwide, only 16 are from Canada. That's 1.5%. Note that meteorites enter the atmosphere at what we call cosmic velocity. That's in the range of 10 to 40 kilometers a second. That's 40 times faster than a fast rifle bullet. In Ontario, we're lucky. We have one of the only all-sky camera networks in the world. It's run by University of Western Ontario. Professor Phil McCausland was here this past February describing it. This network now has 10 all-sky video cameras, which cover most of southern Ontario and stretch as far east as the Cobourg area. Multiple images from these cameras help triangulate and pinpoint the fall ellipse. As a matter of fact, in 2009, this network helped pinpoint the Grimsby fall ellipse. 13 fragments were collected, totaling about 215 grams. That's about the size of an egg. So if you want to learn more about meteorites, the Royal Ontario Museum downtown has an excellent collection. They exhibit all types except some rare ones which the museum does not possess. Unfortunately, you can't pick up their meteorites, they're behind glass. You can handle most of my collection over there with the exception of 2, which are very fragile. Here we see how different types of meteorites were formed. On the left we see the dust from the solar nebula clumps together. These clumps are melted, condensed into little spheres called chondrules. The chondrules clump together with cosmic dust to form boulders or very small asteroids. These are the parent bodies of meteorites we call chondrites. Now the 3 pictures to the right. These planetesimals became large, then they began to melt. The heat was formed by pressure and radioactive decay. The heavier material, metallic iron and nickel and heavy metals, settled by gravity to the center, forming a mini-planet. This process is called differentiation. This is of course how our Earth was formed. When these mini-planets become shattered by cosmic collisions, their fragments become the 3 types shown here. Iron meteorites from the core, stony iron meteorites from the core mantle boundary, and achondrite meteorites from the crust. Note that chondrites can vary widely in composition, depending on which part of the solar nebula they formed. Those that form closer to the Sun are called ordinary chondrites. They're mostly rocky and metallic. Those form closer to Jupiter are called carbonaceous chondrites. They contain water and some carbon-based organic molecules. Out of the 60,000 known meteorites, they can be classified like this: 86% chondrites, 8% achondrites, 5% irons, and 1% stony irons. However, the largest meteorite masses that we discover are irons, and they're the cheapest to buy per gram. That's because irons can punch through the atmosphere without fragmenting, and they weather better once they're on the Earth. Most impact craters on Earth are due to iron meteorites. The largest iron meteorite that's been discovered is the Hoba meteorite in Namibia. It's 60 tons. So this is the last slide about science, then we'll talk about collecting. OSIRIS-REx is a NASA mission launched about a month ago. Its cost is approximately $1 billion. It will study a carbonaceous asteroid called Bennu, approximately 500 meters in diameter. The space probe will first orbit the asteroid and study it in detail. Then it will touch down and grab a sample of dust and pebbles. If all goes well, the sample will be approximately the size of an egg, or a bit larger. In 7 years' time, it will return this sample to the Earth for more detailed analysis. On this drawing, you can see the vacuum mechanism attached to what looks like a pogo stick. This will touch down on the asteroid and collect the sample. Canada gets 4% of this sample. That's our financial contribution to this mission. Scientifically, this mission is quite important. For instance, all carbonaceous chondrite meteorites on Earth are contaminated during their flight through the atmosphere and laying on the ground. So the organic molecules that we see in them may not be the ones that are completely on the asteroid. But this sample collected will be pristine, and it'll help us understand the building blocks of life on Earth and the early formation of the solar system. This mission will also correlate photographic and spectral data that we get from telescopes of asteroids with chemical and physical properties of meteorites. So we have carbonaceous chondrite meteorites on Earth here, but we don't know exactly which parent bodies they came from. This mission will also prove asteroid rendezvous and sampling technology. And lastly, it'll help us accurately predict the trajectory of an Earth-harming asteroid and its properties. And hence, we can determine if we need to deflect it and could we deflect it if it tries to harm the Earth. The dinosaurs did not have OSIRIS-REx and could not save themselves. So here's an idea. We can see the size of asteroid Bennu compared to the CN Tower and the Eiffel Tower. So that's it for science. Now we'll talk about collecting. Let's start with irons. They're actually an iron-nickel mixture with, as I mentioned earlier, some very rare impurities. Usually the amount of nickel is between 5 and 20%. Here we see an iron-sculpted meteorite. This one is from Sikhote-Alin from Siberia, a 1946 fall. Notice the regmaglyphs or thumbprints. These are caused by localized melting of the meteorite during its flight through the atmosphere. Irons that have lain on the ground for thousands of years usually have these sharp features weathered off. Another type of iron is shrapnel. If an iron meteorite punches through the atmosphere and retains much of its cosmic velocity as it impacts the Earth, it basically liquefies on impact. The resulting fragments resemble shrapnel. You can see two examples of shrapnel on the table over there, from Sikhote-Alin, Siberia, and from Whitecourt, Alberta. Most irons, if polished and etched with nitric acid, form a so-called Wittgenstein pattern. This consists of fine interleaving bands of kamacite and tannite called lamella. The kamacite is low in nickel, the tannite is high in nickel. The size of lamella is determined by the percent nickel and by the cooling rate. The larger the parent planet, the slower the cooling rate. Note that some irons do not etch well due to impurities. On the table over there you can see an etched Gibeon meteorite from Namibia. Why would you think it's difficult to counterfeit a Wittgenstein pattern? Well, we can certainly mix the iron and the nickel in the right proportions, but we cannot duplicate the cooling rate needed to form the lamella. It's just a few degrees per million years. Iron meteorites used to be classified by their Wittgenstein pattern. A newer classification is based on the proportion of trace elements in the meteorite, for instance gallium, germanium, or iridium. Here we see a plot of parts per million iridium versus percent nickel. This separates the iron meteorites into classes corresponding to distinct asteroidal parent bodies. Most of the 3,000 known iron meteorites can be classified into just 13 parent planets. I've marked the Gibeon meteorite in red. It's a type 4A, and it's Wittgenstein pattern you can see on the table over there. Stony iron meteorites are from the core mantle boundary of shattered planets. Here's a palisade from Kansas. Pallasites consist of an iron-nickel matrix packed with olivine, that is peridot crystals. Very beautiful. Here's an example of a chondrite. Note the dark but very thin fusion crust. It's composed of melted rock and melted metal formed as the meteorite falls through the atmosphere. These are the most common types of meteorites that fall to Earth. Also on this specimen, note the thin shock veins. This attests to the fact that the parent body really got bumped around up there in space. So chondrites have something called chondrules. This is a characteristic of all chondrites. These chondrules are formed by melting a material in the solar nebula, and they can be between 20 and 80% of a chondrite by volume. The rest is the matrix of cosmic dust. Note that chondrules are not always as distinct as those shown in this photograph. Some have been altered by heat or water. The main minerals of chondrites are olivine, pyroxene with some feldspar, and of course a lot of very rare and unusual elements. Some chondrites, especially the carbonaceous ones, also contain grains called calcium aluminum inclusions, or CAIs. These are important because these are the first minerals to condense out of the solar nebula. They condense at very high temperatures. So these are the oldest minerals in our solar system. As a matter of fact, they can be used to date the beginning of the solar system formation. What scientists have found is our solar system is 4.57 billion years old, with an accuracy of plus or minus 200,000 years. I brought along an Allende specimen. It's on the table over there. You can see the chondrules and also the CAIs in it. Now we move on to achondrites. Note the A. An achondrite is a stony meteorite that does not contain chondrules. Their composition has been changed by the melting and recrystallization process in their parent bodies. They consist of material similar to terrestrial basalts. Many achondrites are called eucrites and consist of basaltic rock from the crust of the second largest asteroid in the asteroid belt, called Vesta. This is an asteroid that NASA visited with a space probe about 5 years ago. If you look at photos of asteroid Vesta, you'll see a massive gouge made by a large impact billions of years ago. About 140 meteorites are known to come from Mars and 160 from the Moon. How do we know this? Well, we've sent spacecraft to these planets. On the Moon, also we brought back samples. The Apollo astronauts brought back about 400 kilograms of moon rock. And the moon rock, in terms of elemental and isotopic compositions, matches almost exactly some of the meteorites we find on the Earth. On Mars we have an extra bit of evidence because Mars has an atmosphere. So some of the atmospheric gases, again elemental and isotopic composition of Mars' atmosphere, matches the gas bubbles in some of these meteorites. So Martian and lunar meteorites are igneous, similar to terrestrial basalts. What's interesting is radiometric dating shows that these are the youngest known meteorites. From the Moon as young as 3.5 billion years old, and from Mars as young as 150 million years. That's when volcanism was still active on these planets. So pulling it all together, here's how stony meteorites are classified, according to their chemical and mineralogical composition. I marked in red squares some of the samples I brought along from my collection. The most common type of meteorite is called ordinary chondrites. This has 3 subgroups, H, L, and LL. This refers to the amount of free iron or iron compounds in the meteorite. Beside each of these letters you'll see a number, usually from 1 to 6. This is the degree to which the chondrules are altered by heat or water in their parent bodies. So a 6, for instance, means that the chondrules have all but disappeared. Carbonaceous chondrites formed further from the Sun. They're similar to clays. They contain some water and some organics, for instance amino acids. Some are like charcoal briquettes and are very fragile. Carbonaceous chondrites can be divided into 7 subgroups of varying composition. For example, the CV, the V refers to the place where it was found, in this case Viggiano, Italy. As I mentioned earlier, OSIRIS-REx will visit a carbonaceous type asteroid. Note that lunar and Martian meteorites are also achondrites. At the Royal Ontario Museum you'll see most of these types except for a few very rare ones which the museum does not possess. For example, down below here, the Chassigny, a Martian type meteorite, only 2 samples are known. Also up here, CI, carbonaceous chondrite, only 5 samples are known. So these can be just as expensive as Martian or lunar meteorites. So how common are the various types of stony meteorites? Here we see a distribution of their occurrence. For instance, chondrites 95, achondrites 5%. The chondrites can be further subdivided into 95% ordinary chondrites and about 5% carbonaceous chondrites. The achondrites, you can see that the eucrites are the most common type of achondrite. Briefly about impact craters. Most impact craters are created by iron meteorites that can punch through the Earth's atmosphere without fragmenting and with most of their cosmic velocity intact. Worldwide there are about 180 known impact craters. Many of these are in Canada. Here we see Meteor Crater, also known as Barringer Crater, near Flagstaff, Arizona. It's approximately 50,000 years old. This 1.5 kilometer diameter crater was formed by an iron meteorite, which was only 50 meters in diameter. There's tremendous kinetic energy at those velocities. In Canada you can see some very old craters and some relatively young ones. For instance, the Brent crater near North Bay, Ontario, or the New Quebec or Pingualut crater on the Ungava Peninsula, and the Whitecourt crater near Edmonton. Craters can be fresh or weathered. For instance, both the New Quebec and the Brent craters are approximately 4 kilometers in diameter, but the New Quebec crater is much more distinct. It's only 2 million years old, compared to 400 million years old for the Brent crater, which is heavily eroded. Another crater is the Whitecourt crater, about 100 kilometers from Edmonton, which was discovered in 2007. It's one of the youngest craters on Earth. It's less than 1,000 years old. You are allowed to hunt for meteorites outside of a protected zone. The protected zone is 200 by 200 meters square. Inside this zone, hunting of meteorites is strictly prohibited, could result in a fine of $50,000 or a year in prison. I've seen strewn field maps published of this site, and a lot of shrapnel fragments have been found outside of the protected zone, where hunting is permitted. Since most of the shrapnel lies buried a few inches into the soil, you'll need a metal detector to find it. This is the last slide of my presentation, briefly about prices and also where to buy the meteorites. So irons are the cheapest types of meteorites because they're the most plentiful in terms of total weight. They start at about 50 cents per gram. So a golf ball sized meteorite can be had for about $150. Chondrites, the prices can vary widely from a couple of dollars per gram to a couple of $1,000 per gram. You may remember some types of chondrites are very rare. Chondrites are still more rare, and they typically start at $20 per gram. The eucrites, I think, are the cheapest type of chondrite on the market. Martian and lunar meteorites start at about $1,000 per gram. That's 25 times the price of gold. The prices of meteorites can also be increased if they have some very special shapes. For instance, if the meteorite was sculpted in a very unusual way falling through the atmosphere, or if the meteorite has an interesting story behind them. Now, where to buy them? A good place to start is the Tucson Gem and Mineral Show. And there are also, if you missed the mineral show, there are dealers in the Tucson area. In in the U.S., there are some storefront dealers. For instance, the Meteorite Museum in Kansas. Try to make sure that the dealer is a member of the IMCA. That's the International Meteorite Collectors Association. In Toronto, there are a few dealers, and if you're interested, I can put you in touch with them. Online, I would only buy from reputable dealers. The best way to protect yourself is to first educate yourself. Thank you for your attention. I'll be glad to answer any questions.